Thank you very much, and welcome to my talk. It's going to be a bit different than the other talk we had this morning and we're going to have this afternoon, because Radiation Solutions is not a service provider. We are instrument manufacturer. So all you're going to hear about it from our point of view, how do you build a spectrometer, because we're dealing with radiometrics, and what can you do pre-flight, as like selecting the right detector, what can you expect on the measurement site? So how do you manage your expectations? Because you cannot beat physics, as been stated this morning already. And then after your flight, when you want to process the data, how can you enhance the signal-to-noise ratio of all your measurements? And I'm going to be talking more precisely about one noise adjusted singular value decomposition. So it's a big word for smoothing out the data and increasing your KUTH sensitivity. And you can actually reconstruct your whole data set with this method to have a much smoother survey at the end, and maybe enhancing some critical areas of your survey. So when we dive right into it, in radiometrics, you have multiple sensors choice. If some of you are familiar with handheld devices, you have different crystal types, whether it's a sodium iodide base, so the first one here, or cesium iodide, or even BGO. They all have pros and cons. What you need to just to remember is, at the end of the day, your sensitivity of a crystal is related to its stopping power, the volume you can have, and also the decay time. So the decay time is whenever you have a photon hitting the detector, it needs some time to be translated into light collected, and then your crystal goes down to a non-excited state, and then you can register another photon. So obviously, the shorter the decay time, the more you're going to be handled, the more you're going to be able to handle a high count rate. So if you know you're going to fly above quite a hot zone, and you don't want to lose too much in terms of recording the count rate coming from the ground, having too much dead time, then you better switch to a quick crystal type. So the density here it's also going to give you the total weight of your crystal you're going to be flying. And usually the higher the density, the more stopping power you're going to get. So you have to find the right compromise. What can you achieve? Because it's all going to be translated into a payload. Do you really want to fly 10 minutes less and have maybe a slightly higher stopping power, or do you want to cover more ground? At RSI, we are specialists in the sodium iodide type crystal, and it came from the very large airborne packs that have been flying either in helicopter or fixed wing that are using 4 times 4x4x16 crystal logs, so a total volume of detection of 16 liters, or even one at the top for accounting for cosmic and doing some cosmic subtraction when you're flying high. And we based all our knowledge on those kind of crystals. And now we are translating that into a 3x3 crystal attached to here a Matrix 600. So obviously there is a big trade-off in terms of sensitivity that you can do between 16 liter to a third of a liter detection volume. But the good thing about it is we're still measuring the same thing. We're still measuring signal coming from potassium, the uranium decay chain, the thorium decay chain. So when you look at spectral data, that's what we're going to see. You're going to see, for the potassium, just a peak sitting at 1460 keV, then the scattering. And you can also tell that depending on the altitude you're flying at, you have some shapes that are not exactly the same between the low to a high altitude. But the peak of the potassium will always sit in the same region of interest. And the same goes for the uranium decay chain. You just have much more peak you could look at, but we traditionally look at this peak here around 1600 keV because it's not influenced by any other peak close by. And the same for the thorium. We are looking at its very high energy range. And the way everything works when you want to translate those counts into concentration is you have to account for the influences of one isotope or one energy band into the other isotope's energy band. And you can do that using stripping ratio, which I'm going to go to in a moment. But if you were to isolate the contribution from either pure potassium signal, pure uranium, or pure thorium, you could end up with exactly the type of crystal I showed you earlier with a 3x3 with this blue, orange, and gray spectrum. So that's what you're gonna be trying to extract from any points you're recording with the sensor to convert those count rates into percentage of pp or ppm. And the way it's done, it's the same method for the big packs that have been used since the 70s, using an IAEA standard calibration method, just adjusted to the small size crystal we're going to now be flying with a 3x3. So here's a few pictures of how it looks like. It's a 1 meter by 1 meter by 30 centimeters deep concrete pad that is mixed with, so you have a set of 4 pads. One is just the concrete you're using to mix everything. Another one is the same concrete with added potassium signature, another one with some uranium, another one with thorium. So you should know when you're cooking those pads exactly what did you put in as a signal, as concentration for the different potassium, uranium, thorium. So then knowing your reference pad, what's the initial concentration is, you can know the net concentration you've added, and you can use that to get the sensitivity and the stripping ratios from for this particular crystal you're looking at. Another important thing to consider is the geometric correction factor. When the crystal is sitting in the center of those pads, it's not equivalent to an infinite source that you'll be most likely looking at with a crystal. You're only looking at 50 centimeters on each side. So you have also radiation coming from outside those calibration pads that are gonna be recorded. So you need to correct for that. Not gonna go too much into detail, but it's equivalent to an E2 formula, but you can see that actually those pads are roughly 83% of an infinite potassium source, uranium source, and 81% of thorium infinite source. So you just need to have that in mind as well when you are reprocessing the data later on to make sure your calibration is correct. And when you enter those stripping ratios, which are basically the influence of thorium into the uranium window, influence of the uranium to the potassium window, and also the thorium into the potassium, you end up with a bunch of numbers here that are not that important today, but when you're processing the data required, you're using that to process and end up with the net count rate from potassium, uranium, thorium on a point-by-point basis. Also, when you're doing the calibration, you end up with a very important factor, which is your sensitivity. So how many counts per second, net count per second, should I say, are you getting per percentage of potassium or ppm of uranium and thorium? So that can give you already an idea of, okay, if I want to detect so many ppm at contact, so everything is done at contact here, what can I expect as a count rate? And also a good thing to do is to double check that, okay, once I get all those numbers, if I input them into my detector and I'm redoing the measurement on the pad, am I ending up with the same value as my calibration sheet says? And yeah, we're pretty close, we're pretty spot on. So that's always a good check, because if you see here a big difference, then it means something went wrong. Either you had a bad measurement, you didn't take the right measurement into account, the crystal might have cracked in between. You have all sorts of issues that you can spot right there. So let's say now we have the stripping ratio, that's nice, you get the sensitivity, and you also need to account for the cosmic, because all cosmic radiation that you're gonna see, it's also scattering, and they're gonna pollute your thorium, uranium, and the potassium windows. So the only way to measure that is to go on a lake or very far off the ground, so you don't have a contribution from the ground itself, and you're just measuring, okay, what do I see from the sky? So I went on Lake Ontario about 2 kilometers away from shore, and that's what I measured. I normalized to 1 count in the cosmic window, so it's a high energy window, and then I'm looking at everything else that I'm seeing. And you can tell that for every count in the cosmic window, I'm getting about 0.09 in the potassium windows, 0.05 in the uranium, and 0.04 in the thorium. So you do have influence of the cosmic into your ground element. So you need to strip that out as well to correct for the cosmic and not ending up with a higher concentration that you really have. So that is quite important to do. And you don't have to do it for every crystal. This response is pretty uniform across everything. So now you have to know, okay, what can I expect as a measurement? Because I cannot just go in blind and get some data and say, okay, it's good, we got what we measured, or am I actually measuring what I'm supposed to? So here's just a small example of, okay, we are flying over an area which has some uranium. I took 5 ppm background of uranium, and I want to see if I can detect a stripe that is 2 meters wide. And I put different intensity of the uranium. But anyway, that's going to come later. But how does it look like from the detector point of view? So as I mentioned earlier, you get radiation not coming only from below the detector, also from the side. So where is the signal coming from when I'm measuring into a given position? So you can compute, okay, what is the where is the radius that I'm actually looking at with the detector? And you can tell that if you're flying at 10 meters, 80% of your signal is coming from a radius of 20 meters around you. So that gives you quite a large area you're looking at. And obviously, the higher you go, the wider you're going to look. So the stripe or whatever you're trying to detect is going to be blended in your background or the surrounding. So that can lead to deceivingly low value or significance of a measurement you're going to get. So if we use that assumption, we know exactly where the radiation is coming from. That's the field of view of my detector. So I'm looking around, let's say, for 10 meter high, 20 meter here. And then my stripe is actually 2 meter times 2 times 20, so 80 square meter. So that's what you can compute here. Okay, I'm going to measure this different proportion, and I'm also going to put a bit of height attenuation. This can be worked on and determined empirically. I'm just going to use the same as the 16-liter pack from the AE report because I don't have any more data than this one. So, and you can see also that at the different altitude, when you use that your CPS per ppm of uranium start to drop quite dramatically between 10 and 50 meters. You're losing 1/3 of the sensitivity when you're flying higher. So this is all the response from the detector from a mathematical point of view if everything is perfect. So when you look at the average ppm that I'm looking at, so both the surrounding and the stripe, you can see that even if you put a stripe at 150 ppm, you're only looking at an average of, let's say, 7.5 ppm in the whole field of view. And of course, the lower you fly, the more, the higher the ppm you're going to see. And it's not a lot you're looking at really when looking at a big area. So you better fly as low as possible if you want to find very small spatial vein or even hotspots. And that's translated, these curves here translate into around 2 to 12 counts per second, depending on your flying. So you're not relying on a lot of statistics. So you know already that you're going to end up with a lot of statistical noise that you're going to have to remove one way or another when doing the post-processing of the data. And then if let's say you're trying to look for those kind of veins, so you're going to fly mostly over background, and then all of a sudden you'll see a spot that is slightly different, maybe 2 standard deviation above what you found before, and that's going to be equivalent to 150 ppm stripe. If you have a 300 ppm and you're flying at 20 meters, it's going to be just above 2.4 times the background, standard deviation of the background, and so on. So you're looking at very fine features in the ground, in the survey. So you have to keep that in mind and manage your expectations related to the height and speed of what you're flying over. So now that we established that, yeah, the signal is not that strong, how can you improve it? So sorry, there is less pictures, more math here, but basically you're looking at the data set, the spectral data set. So you have 1024 channels of the spectral I've seen from above, like a bird's eye view. And it's going to look like that in the linear space. So here's the potassium, uranium is barely non-visible, and thorium neither here. But yeah, you take the whole data set and you're going to ask yourself, can I translate that instead of using 1024 spectral data? Can I actually build another base to represent my data set? And that's basically what's done here. So you're aggregating all the data and you're going to describe your data set not by saying, oh, I have so many times the potassium, so many times the thorium, so many times uranium. You're saying, oh, I'm getting so many times this particular mix of potassium and thorium, then I'm going to remove that from my data set and look at the residual. And you're going to describe your data set by doing that. So you're constructing a new base of vectors to describe your data set. And so this new base is here in the U. This sigma matrix are the eigenvalues. So how important is this given new vector base important to describe your data? So if you can cut off your description of the data set by going, okay, I just need the 3 first eigenvalues because for me they are the most relevant. So, okay, I'm cutting here, I'm using the first 3 here, and I get my concentration for each point there, so you can reconstruct the data. You can choose 1, 2, 3, 8, as many as you want. And what you end up with is, instead of having this blue 1-second spectrum that is very noisy where you cannot see anything, when you reconstruct the same spectrum with the NASVD results, you end up with something much more smooth. And you can actually see the potassium peak. I should have put it in log scale to see the uranium and thorium peaks. But you have a cleaner signal to work with and go back to the concentration of the different elements. And if we look at the potassium uranium windows, that is before the flight and the processing with NSVD, and that's after. So which one do you rather work with, this one or that one? That is a pretty straightforward answer, I think. And then when you put that with the sensitivity factor, the altitude attenuation to project yourself on the ground or what is actually coming from the ground at contact, then you can do the maps. So the values are, I would say, not very important, but that is before and after. So you can see a little bit more finer details of different areas. That's for the potassium. For the uranium, you clearly see different spots, different areas that are blurred in there. And for the thorium, it's the same. So that's what I had to talk to you about. Just remember, manage your expectation, know what you're flying over, and also don't forget to post-process the data, otherwise you'll have huge noise. Thank you.
I've got a question for Lucy. She's and Doug. Hey, stop, pay attention in class. I would call that processing inversion that he was just talking about. Wouldn't you?
Well, I think I'd still list that as processing because you're still getting a representation of the data. Whereas if you're going to invert, then you might want to get, let's say, a plan map of the remaining concentration.
Well, just to clean up the data. So that's a processing stat is not an inversion. I thought it was more like an inversion myself, but anyway, I stand corrected. Anybody else got some questions? Here's one.
Just some quick clarification. On your slide where you use like the eigenvectors to break apart your components, how is this explicitly different from like a principal component analysis where you're just taking the first couple modes of variance and reprojecting the data?
Yeah, you're right. SVD is pretty much a PCA. It's just the way those matrices are built with the triangular. They have to be triangular and they have to be orthogonal and orthonormal, which PCA doesn't require necessarily. So the SVD is different into that point, but you could do a dirty SVD or PCA by just, you take the average spectrum over your whole data set, you subtract that from your data set, and then that could be your first component, your first order. Then you take what the residual, you do the average of all your residual, we subtract that. That could be another, it's just quicker and dirtier because you lose those functions and you don't have any criteria to select how important the eigenvectors are. But yeah, PCA, SVD are in the same family of data deconstruction and reconstruction, yes.
You're applying that to every, then you're going to apply that to every pixel on your raster, which then you project it into geographic space.
Yes, yes.
But you train like this model on just a subset of your data, or is it?
No, you have to take the data set as the whole, and then you reconstruct this data set with that. If you introduce new points, then you might have another feature in that point that is not described by those features. So you end up with something that's not represented. You actually won't see this extra feature, this new feature using that description. So you're losing data. You have to use the same data set for both the training or decomposition and reconstruction, yes.